potential energy to kinetic energy. To begin with, let's go back and review potential energy. Remember, you have potential. So potential energy is given the symbol U, capital U, and this is a specific kind of potential energy that we'll be talking about called gravitational potential energy. So this is really one big quantity right here. And potential energy is equal to the mass of the object, in this case a bowling ball, and times the acceleration due to gravity, 9.8 meters per second squared, and then how high the bowling ball is raised plays a role as well. Remember, potential energy is the energy due to position or arrangement. So the arrangement of the bowling ball above Dan's foot is what's causing Dan's concern. And also remember that all energy is measured in joules. So maybe we can take a realistic look at the release of this potential energy.
Dan really shouldn't be concerned about the bowling ball's potential energy. He should be concerned about what happens when I release that potential energy.
So, starting back at the beginning here, before I released the bowling ball, Dan was concerned because intuitively he knew the bowling ball had a lot of potential energy. And then when I did release the bowling ball, that's when he should really have been nervous, because that potential energy starts turning into a different kind of energy. The potential energy starts to decrease because the height's decreasing, and gravity is doing work now. The potential energy is being converted into work, and that work is turning into the kinetic energy of the bowling ball. The bowling ball is getting faster and faster. So as it falls, potential energy is decreasing, but kinetic energy is increasing. And again, less potential is turning into more kinetic, more kinetic, more kinetic, and right before it hits Dan's foot, the potential energy is barely existing, and it's turned into almost all kinetic energy the instant before it hits his foot. And then, boom, ow! It hits his foot, and notice, it looks like all of the energy has disappeared. But it hasn't disappeared, and we'll talk about that at a later time, where that energy would have gone once it hits Dan's foot here. But back to the conversion between potential energy and kinetic energy, let's take a look at that and how it looks mathematically. So now into kinetic energy. So remember that kinetic energy is the energy due to an object's motion. So we had potential energy that through the gravitational field, when the ball was released, the gravitational field did work to convert that potential energy into kinetic energy. So we started with potential energy equal to mgh, and again, as soon as we released it, it's no longer potential energy, it's gravity doing work. And gravity accelerated the mass of the bowling ball through a distance here, and so that was the average force times the distance. And recall that distance, when we had accelerated motion, was equal to 1/2 at squared. So if we plug that in for the distance d right here, then we have mass times acceleration times 1/2 times acceleration times t squared, combining like terms so that we have an a squared and also a t squared. We have a times t total quantity squared, and so our work is 1/2 m at squared. And recall that v is equal to at. So if we plug in for the at squared here, we plug in a v right here, we will get our final equation for kinetic energy, and it is kinetic energy is equal to 1/2 times the mass times v squared times the velocity squared. And that's our kinetic energy equation. And it should make sense because kinetic means motion, and we have an object's velocity in the equation, and also the mass of the object should play a role, like it does in this case, being a massive bowling ball. So please note this derivation. So to summarize, what we saw that gravity did work to accelerate the bowling ball, pulling the bowling ball down, and applying an average force through a distance, the height that the bowling ball was raised. And that work that gravity did causes a change in the kinetic energy of the bowling ball. And when all the work is done, all of that work would have gone into creating a lot faster bowling ball. And the energy due to an object's motion is kinetic energy. We thought to help with these problems, we would approach them by being a little smart. Get it? A little smart? Anyway, we want to take a look at kinetic energy, and we want to look at that in a side-by-side example to show off the really important aspect of kinetic energy, and that is the relative velocity in this case. So we're going to start with our first example up here and our kinetic energy equation that we just derived, 1/2 the mass times the velocity of the object squared. And so when we plug in our numbers, our smart car has a mass of 800 kilograms, and we multiply that by the 0.5 or the half, and then we also have to multiply by its velocity squared. So it's just the velocity part that's being squared here. So that's 18 meters per second squared. And once we're done with our multiplication, we get 129,600 joules. Remember, all energy, including kinetic energy, is measured in joules. So that's a very large number. But the part that we wanted to emphasize, and the reason this looks so identical, is because it is identical except for one thing. We are going to double the velocity in the second example. So we go from 18 meters per second to 36 meters per second, doubling the speed. When we do that and we plug it back into our kinetic energy equation, the only thing that changed was the speed, and it was doubled. But when we square doubling, that actually causes quadrupling. So now look at the total energy. It is quadrupled. It has gone up 4 times. So when you double your speed, you actually are increasing your kinetic energy by a factor of 4. So that's an incredible amount of energy increase. Let's take a look at one more system where work is going to cause a change in kinetic energy and create a very large kinetic energy. So electric motors are going to start this system with this big chain, and they'll hook up to the roller coaster. And once they hooked up to the roller coaster right there, the electric motors are going to do work. And they're going to lift this roller coaster. Wow, that's so steep. They're going to lift this roller coaster, lifting its weight, mg, a particular height, h, and giving it potential energy, mgh. So when the roller coaster gets to the very top right here, work will have changed its position and therefore given it potential energy. And now, right before it starts to go, it has potential energy, and then that potential energy is going to be converted into kinetic energy by gravity doing work. So gravity starts doing work and converts that energy into kinetic energy, and then it keeps sloshing back between potential and kinetic, and then back to potential, and then back into kinetic, and then back into potential, and so forth as you go round and round the roller coaster. And Scratch's parting thought? And good luck on your quest for continuous improvement.